This segment discusses the composition of components into larger computations. We introduce a symbolic specification which specifies how the components are constructed, and we verify that symbolic specification solely in terms of its logical relationships. And then we show several implementations of the specified computation with differing structures and differing behaviors, all of which faithfully realize the specified logical behavior. We've discussed 2 or 3 of these, and then there's a spreadsheet in the directory that compares all the implementations with each other. Finally, we have a circuit that is large enough to illustrate what logically determined means. So we pick one of the circuits and we take one of the gates in the circuit and we vary that gate through the delay of that gate through 2 orders of magnitude and demonstrate that the circuit runs over that whole range of delay. Now some details. We'll begin with the half-adder component. These are the tables that define the half-adder with A and B input and sum and carry output. These are the equations mapped directly off the table. Since they're mapped directly off the table, we know that the equations fulfill the completeness criterion. In other words, that they're flow sufficient. Whenever they have an input, they will generate an output. This is the component wrapped around the set of equations, and it has A and B as input and generates sum and carry out as output. So the flow sufficiency of the component itself will be deferred through its boundary half oscillations. In other words, the component is flow sufficient if its boundary half oscillations become flow sufficient. So these are the canonical minterm forms of the equation sets, and we can optimize this in a couple of ways. One is to combine the minterms as common subexpressions, which we did down here, so we're getting both sum and carry out off a single minterm. And the other is to optimize each one individually, which is what we did here. This is essentially a Boolean XOR, and this is a Boolean AND. There will be circumstances where it will be useful to propagate the carry out before the carry in arrives. And there are circumstances where we can know what the carry out will be before the carry in arrives. So if the B is the carry in here, and A is 0, then we know that the carry out is going to be 0, and we can just go ahead and propagate the carry out. And that's what this logic is doing. So we've replaced the Boolean AND here with a logic that allows the carry 0 to propagate ahead when A is 0. So when the carry plays ahead without waiting for B, it does not imply the completeness of input and therefore does not fulfill the completeness criterion. However, the sum does require both A and B, and when the sum is complete, it does require the completeness of input. And the sum and the carry, the completeness of sum and carry, together imply the completeness of resolution. So the 2 of these together imply the completeness of input and the completeness of resolution, fulfilling the completeness criterion. Now with this first circuit, once the carry propagates, then the carry in will come along later, and when A becomes null, the carry in will hold this gate at data. And so while the circuit played ahead with the data transition, it will not play ahead with the null transition. So we have another circuit down here which isolates the carry in from the generation of the carry out, so that when if A generated the carry, when A becomes null, the carry out will become null also. So we'll call these half-adder A and half-adder B. And the minterm from the previous page was half-adder C. So we'll use all these half-adders in several different examples of different structures of counters. So we're going to make a counter, so we have to cycle the sum of the count around the counter back to its input. And we'll do that by putting the counter in a ring. And we'll construct the ring of 4 components. The half-adder is 1 component, and we'll have 3 buffer components. And we're going to initialize a data wavefront. We're going to initialize A to 0. And these are the components that will do the initialization of A to 0. So this is the specification, right? So we have the 4 components, the half-add component, and the 3 buffer components. And you'll notice that the count, the output of the half-add, flows to D flows to A flows to B, and B flows to count. So we have our closed ring with a half-adder in it. Now, the ring is sufficient flow because there's 4 oscillations in the ring and only 1 data wavefront initialized. So the flow sufficiency of this component again defers to its boundary half oscillations, which is carry in, where are we here? Carry in, count, and carry out. So this component is internally flow sufficient, so it's ultimately flow sufficient if its boundary half oscillations are flow sufficient. So we'll construct a ring for each half adder, and these are the Verilog files for the ring for the A half adder and the B half adder and the C half adder for the 2D counter. And we'll construct a variety of counters with very different behaviors. Now we're going to make a counter by connecting our half adder rings together. And we're going to start by defining a path structure with a token count, and we'll define it to be 32 AND related components, each of 2 rails of OR related. So this is our dual rail, and this is 32 dual rails, so this defines a 32-bit dual rail number. Next, we're going to structure the path with the digit counts, and we called our ring, we called digit count over here. You didn't notice. So we're going to refer to digit count, and we're going to structure our ring with the first component, structure component of count. And so that's going to be I, and I is going to range from 0 to 31. So for all values of I from 0 to 31, we substitute this, and then we connect the corresponding names. And what that gives us is a stack of 32 half adder rings with the carry in connected to the carry out connected to the carry in through the stack of rings. Now, the half adder rings were sufficient flow given that their half oscillations were sufficient flow. So when we connect the carry half oscillations, they were sufficient flow. So now we have a new component which is sufficient flow internally, and its ultimate sufficient flow is deferred to the half oscillations on its boundary. And the half oscillations on its boundary now are the first carry in, the last carry out, and the sums, the 32 sums. So over here in the same statement where we structured the half adder rings, we also define the first carry in to be 1, and that's a constant component, and that constant component connects to carry 0, so that closes carry 0 with sufficient flow. And then the last carry out, we connect to an auto consume. So this is a sync component. Okay, so the last carry out will be sunk. So we've taken care of those half oscillations, and what we have left is a component that is sufficient flow if its 32 sum half oscillations are sufficient flow. So the next thing we do is to the 32 sum oscillations, or count, or they're called count here, to the 32 count oscillations, we sync them, all 32. So now that we've closed all 32 count outputs with an auto consume, we have a completely contained component there are no more half oscillations on its boundary. It is sufficient flow. Internally, the rings will flow all by themselves. So we have a self-contained component that once it's started will flow forever all by itself. What we've constructed is a stack of 32 rings with a carry pipeline running orthogonally through the rings from ring to ring. And as a carry pipelines to each ring, the ring generates a digit of a count. Now, as successive carries pipeline through the stack of rings, successive digits of successive counts peel off the stack of rings. And this is what that looks like. This is the first count peeling off the rings, the second count. Each count is separated by a null wavefront, you'll notice. So they're all logically separated. And as the last digit of the first count is peeling off the stack of rings, we see that the first digit of the 1, 2, 3, 4, 5, 6, 7, 8, 9th count is just entering the stack of rings. So we have 9 counts simultaneously spiraling through the stack of rings at different stages of completion. Now, as a test bench, we run the counts into display sum, which is a 64 rail variable, which is the 32 dual rails. And we'll look at that so we can see the count. And now if we shrink this down, we can see that it's counting, right? This is bit 0, this is bit 1, this is bit 2, bit 3, bit 4, bit 5, bit 6. And we can see by inspection that the counter is counting correctly. So this first implementation we looked at is the canonical mapping of the symbolic specification. It's the direct mapping of the specification itself. But we can make a lot of changes to the mapping, variations with less hardware, change the oscillation structure, and so on and so forth, all of which maintains the faithful implementation of the symbolic specification. In other words, preserves the behavior specified by the symbolic specification. So we'll look at a few of those. The first one we'll look at is to remove this link for the carry pipeline. And the carry pipeline works in a slightly different way, but it still works correctly, and we've saved a little bit of hardware. So this is what that looks like. So now this is the Verilog programs that implement it. Now this behaves pretty much like the previous one we looked at, so we're not going to dwell on it. What we're going to do is we're going to go to the imposition of full token completeness. So down here where we specified the close the count, we didn't specify exactly how to do it. In the previous one we closed each digit individually. Now what we're going to do is take the completeness of all the digits. So we're going to take the OR, the AND of all the ORs of each digit. We're going to AND them all together with a big AND tree, and we're going to get a single signal that's going to fan out and close with all the digits. So that's going to effectively close the count, but it's also going to require that all the digits be complete before we do the closure. So we're imposing full token width completeness, or full word completeness, and these are the Verilog programs that implement that. There's another one for C here, actually. This is what full word completeness looks like, and this is with half adder C, which doesn't have any play ahead for the carry ripple. So with the data transition, we wait for the full carry ripple before we allow the null to begin, and then we wait for the full null ripple before we allow the next data transition to begin. So the thing you notice is that we can drop a time instant between each count. And that's what full word completeness allows us. But this is very slow. We're doing a lot of waiting. Now, if we use half adder A, then it allows the carry play ahead for the data transition, but not for the null transition. So since all the inputs are 0, you'll notice that the carry for the data transition happens almost instantaneously, and then we wait for the carry for the null transition. We'll spread this out a little bit. We have to wait for the carry ripple for the null, and then we can begin the next data transition. And you'll notice again we can drop a time instant between each count. Now with half adder B, it allows the carry play ahead for both the data transition and the null transition. We'll spread it out here a little bit. So the data transition is almost instantaneous and the null transition is almost instantaneous. And we can still drop a time instant between every count. Okay, but now this is much faster. So if we equalize the times on each of the versions, so this is the half adder C, this is about 5 nanoseconds between counts. This is with half adder A, and it's about 2 nanoseconds between counts. And this is with half adder B, which is a nanosecond or less between counts. So you can see that the carry play ahead gains us a lot of leverage for the full word completeness case. Now there will be carry chains that won't play ahead, and we'll have to wait on them. And we see one here. Here's a short carry chain where it won't play ahead, and we have to wait on it. So we have to wait a little longer here than we did over here. But these are usually fairly short. Now if we look at the display sum, we can see that the counter is still counting just like it always did, bit 0, bit 1, bit 2, bit 3, and so forth. So in the last two circuits here, we'll integrate the combinational logic with the flow control logic. So this is the component, and this is the combinational logic, and this is the flow control logic. And what we'll do is to integrate these, and we'll run the enable into this rank, and we'll still have the completeness. So now this is the integrated half adder component, and this is running into this rank. Now this was these TH-OR gates, THX-OR gates were 4 input gates, and now they've become 5 input gates. So we've added this to the library, and we can do this in the simulation. 5 input gates probably don't make sense in CMOS, but we'll do it here just to illustrate a point. So now this is the enable rank, and it's also doing the combinational circuit, and here we've integrated this with these gates, and now this is the integrated combinational logic. So now we put the half adders in the rings and in the structure, and now in this structure, the counter circuit, there are no gates that are only doing combinational duty. Every gate in the circuit is doing flow control duty, and some of those gates are also doing combinational duty. But the control and the combinational logic is fully integrated in the circuit. So the next one, we take the min-term half adder C, and this has 2 stages of combinational logic. So we'll make each stage a control stage, a link. So here, this is the one of ones become a link, and then we have the completeness of those, and that goes back, and the 2 of twos become a link, and then we have the completeness of that, and that goes back. So now we've turned this into a two oscillation pipeline, in contrast to a 1 stage of pipeline oscillation with combinational logic in it. Okay, so now we integrate this into the rings, and this is our fully integrated counter with half adder C. So you can these behave exactly the same way as the others. Now this one, this gate is going to be much slower, so this is going to create a slow oscillation, and that's going to slow the whole thing down. So this structure is going to be a little bit slower than the fastest structure. This structure has less delay in each oscillation, so this is going to turn out to be the fastest counter of all the circuits, and also the most efficient. We have a large enough circuit now to illustrate what logically determined means. So we're going to choose a gate in the half adder A, the TH23W2 gate, and we're going to change the delay on it and simulate with the gate with a different delay. So in the library, the TH203W2 is set at 40 picoseconds. So we're going to set the gate at 4 picoseconds, and we're going to set the gate at 400 picoseconds. So we're going to vary the delay of the gate through 2 orders of magnitude. So the simulation that's up here is the simulation with the gate at 4 picoseconds. And it's pretty much identical to the simulation with the gate at 40 picoseconds. Making a gate fast in relation to a bunch of slower gates really doesn't change anything. The fast gate ends up waiting on the slower gates. So next we change the delay of the gate to 400 picoseconds, and we ran into a little difficulty. So anytime you're increasing the delays in a system, you have to take into consideration the init, because the init might not be long enough anymore, which is the case here. You can see that the initialization is progressing and validating signals up to here, and then the init goes low, and it goes everything goes kablooey. So we had to extend init. So we extended init to 20 picoseconds. It was 12 picoseconds before. We extended it to 20 picoseconds. And here was 12 picoseconds, and you can see that the init wasn't completed, but you can see now that the init did complete at about 14 picoseconds, 14 nanoseconds. And so when it goes low at 20 nanoseconds, the system is initialized. And after it goes low, the circuit behaves pretty much like all the other circuits it did, except that it's running much slower. If you look up here, we'll see the intervals. This is 1070, 1080. So the interval between counts is well over a nanosecond now, whereas before it was in the 400 picosecond range. So the long gate has slowed down the circuit, but the circuit is still working logically correctly. If we look at the count, we can still see that it's counting correctly. We don't get as many counts as we used to because it's running slower, but it's counting correctly. You can play with the gate delays in the library however you like, change them to whatever you like, except 0. I think that might break the simulation. Try changing them all to 1 picosecond and see what happens. If you manage to break a sandbox circuit with a delay, please let me know.